please, I want you to take a look at your objectives here, thank you, for section 1.6. This is going to be a 2-day section. By no means will we get to all of this. It's an advisory schedule today, and we went over your tests, so that's okay. We don't have, tons of time to get through everything that we need to get through. But it is one of those topics that you have seen so many times, transformations, bless you, that a lot of this is going to feel reviewish and kind of old hat. But there are some new glitches in here too. So we might get to the glitches depending on how we do for time today, and we just might not. So we're going to determine the type of transformation based on a graph or equation. We're going to talk about the vertical and the horizontal translations. If you remember, H is our horizontal translations. That has to do with the right and left. And then K is our up and down, our vertical, in our formulas that involve A, H, and K. Reflections across the x-axis, we're going to see a negative in front of the y for those. And then reflections across the y-axis, we're going to see a negative in front of the x. Always opposites with reflections. Then we have vertical and horizontal stretches and shrinks. That's part of A. A tells us whether or not we have a stretch or a shrink, because if A is bigger than 1, it's a stretch. And if A is a fraction between 0 and 1, we're looking at a compression. And then we want to graph combined transformations based on the parent function graph of the equation. And yeah, we'll probably use the calculator for the ones we're going to do today. And then write an equation for a combined transformation. Well, yeah, once you know how they work, you should be able to take a basic parent function and use the transformations to get a new equation for that function. So types of transformations, up here it says, these leave the size and shape of the graph unchanged. I'm going to have a little new piece of vocabulary here. That's called a rigid transformation. So basically it means you're just taking this graph and you're sliding it somewhere. So that's horizontal translations and vertical translations and reflections, because if you turn it upside down, well, it still looks the same, it's just upside down. So the basic shape is staying the same. But when we've had an A value that makes something either wider or skinnier, then those are going to be non-rigid transformations. And rigid just means something that doesn't move, is considered rigid. So non-rigid, this would be where we talk about A and its effects are a lot like taking a rubber band and holding on to the bottom of the rubber band and the top of your function. And when you stretch it, you're pulling that rubber band up. So it affects the way that the graph looks. Or if you compress it, pushing it down, it's going to widen it out. So horizontal stretches or shrinks, that's going to be new to you as well. You've never done the horizontal stretches or shrinks, but you've done the vertical stretches and shrinks before. So the general rule, changes inside the function with the x are horizontal. That's what we mean by inside the function. If it's connected to the x, it is related to x when you graph it. And that would be going right and left. So those are your horizontal translations. Changes outside the function are going to be vertical. And that's always where in our formulas we've had that plus k hanging out in the back. So that's our shift up and down when we do these. And again, H and K, they've been so helpful all the way through Algebra 2 talking about A, H, and K. So translations, let C be a positive real number. The following transformations result in translations of the graph of f of x. If it is attached to the x coordinate. Notice they're not using H and K anymore. They can use whatever letter they want to use. We have to remember that x responds differently to translations than y does. So when we look at this, this is actually the opposite of what we would think. If this says -3, that means it's going 3 units to the right. We see a -3 and we think, okay, that's got to go 3 to the left. But x responds in an opposite direction. So a translation to the right by c units will give us x minus c. So plus c is actually going to take us to the left. So whenever it's attached to the x, always think opposite of what I see. Vertical translations, well, that's normal. That just totally makes sense. If you add after you already have the function, it's going to go up. If you subtract after you've already had the function, it's going to go down. So K is really intuitive. H is the one where we have to do a little thinking about the opposites. And these get us right into it. It says, describe how the graph of y equals the absolute value of x can be transformed to the graph of the given equation. So they're just asking us to describe those transformations. You know, what happened to this? So we're comparing y equals the absolute value of x. And we look at that and say, hey, there's a -4 on the back. Question, is that -4 attached to the x? So that's not an h value. That's not a horizontal shift. This is saying down 4. So translate down 4 units. Now we could have easily said shift down 4. But that's another AP skill that I want to get across to everybody. Translate is a geometry vocabulary word. And that comes across to somebody that's grading your test as, hey, this person really knows what they're talking about. They didn't just say shift. They know that translate means to slide it. So this one over here, comparing that to the absolute value of x. Is that 2 attached to our x this time? Yep. So we think, okay, that's the one where I have to think backwards. So +2, I'd normally think is to the right, but this will actually be translate 2 units to the left. So that's the one that's always good. I can say it till I'm blue in the face, be careful about H, be careful about H, but somebody will mess it up. You know, they just will. It's human nature, you know, to go with what we see. Alrighty. So now, each view in figure 1.74 shows the graph of the cubic function, parent cubic function, y equals x to the third, and a vertical or horizontal translation, and that one they're showing as y sub 2. Write an equation for y sub 2 as shown in each graph. Well, let's see. The dashed one is our helper, and that's going to be the basic parent function y equals x cubed. So what we really have to do is figure out how they've translated this, and then whether or not we should connect that with x, or if that's something that happens with y. So here was x cubed, and now it's 1, 2, 3 down. Down. Does that affect our x? Nope. Bless you. So we don't use parentheses. We don't use grouping symbols. We just say, hey, here was x cubed, and we moved it down 3. All right, now this one started at 0, 0, and suddenly it's over here at -2, 0. So that means this moved 2 to the left. Does that affect x? Yes, x is right and left. So that means I'm going to have to do something with x. That was interesting. There it goes. Because I'm moving right and left. What should go in there if we want to move to the left? Is a +2. Always the opposite of what our intuition tells us with x. So that would be a +2. On this one, we go from 0, 0 over here to 3, 0. Is that going to affect my x? Yep. So to make that move 3 to the right, what do we put in there? -3, yes. So that's the most important part of this, is really just remembering whatever I do with x, I have to think opposite. And you could go back to your days of Algebra 2 for that thinking and say, hey, if my parent function is a cubic, I'm going to need y equals a times the quantity x minus h cubed plus 2, plus k. It all depends on what we're going to do with the individual problem. So reflections. The following transformations result in reflections of the graph of y equals f of x. If you want to reflect across the x-axis, you have to make the y negative. Okay, Cedarholm, that's not the y that they made negative. They made the f of x negative. Well, here's what they did. Then they solved for y, because that's what we do. we always get y by itself. So they divided both sides by -1. And there it is. So when we reflect across the x-axis, it's actually the y that was made negative, but when we look at it, we realize, okay, it's negative of the whole function over there. Across the y-axis, only the x is negative. Only the x becomes negative. Through the origin, both of them, you know? You take any point, 3, 3, you want to reflect it through the origin, -3, -2. So 2 negatives there. So x-axis, change the y's. Y-axis, change the x. The origin, change them both. So finding equations for reflections, it says find an equation for the reflection of f of x equals 5x minus 9 over x squared plus 3 across each axis. Okay, well, let's see. Let's just start with the x-axis. Let's do this in alphabetical order. So if we want to make a reflection over the x-axis, which one gets the negative? Reflecting over the x-axis, which one gets the negative? Peak. There's our negative in front of the y. So let's go down here and realize this is the y. And to reflect it, we're going to have to slap a negative over here. Now normally we would say to get rid of that negative, hey, let's just divide both sides by -1. But on the other side we have a fraction. And it's just as effective to multiply by -1 as it is to divide. So to get rid of this, we would multiply by -1. Now -1 is -1 over 1. Our negative and negative on the left-hand side are going to cancel each other out. So really what we need to do is distribute a negative to our numerator. And only our numerator. We use the negative on the top, we can use the negative on the bottom, but not both. Pick what we're going to use it for. So that one would give us -5x plus 9 over x squared plus 3. Over the y-axis. What do we do to reflect over the y-axis? You were already doing it. Make that x negative. And then we simplify. You know, this was something we did when we were trying to figure out whether or not we had even or odd functions. So we realized that this will be a -5x minus 9 over x squared plus 3. And that'll do what we need to do. Now, notice I have labeled these just as y. And that's because we don't really have a special symbol that we use for reflecting over the x-axis and the y-axis. So better to just stick with something really generic and just leave your x's and y's on there when you're talking about those reflections. And they did just ask us to do this for the axes. It did not say to reflect through the origin, but certainly we could change the signs on both sides and see what happens. But graphically, we should see, hey, this should be flipped over the x-axis. This should be flipped over the y-axis. We should definitely get a feel for the fact that what we did was correct. It's another thing where before you turn your test in, you say, you know what, I'm just going to graph these real quick and see if they really do look like they're reflected over the x-axis and the y-axis, and make sure that what I have is accurate. So what we're doing here is we're saying, here's the red one. If you flip that over the x-axis, yeah, it would look like that because the x-axis is going to provide that equal but opposite piece for distance that you learned about in geometry. And over here, equal but opposite from the y-axis. You should see that flip as you move through there. So visually, you want to verify what you already know to be true from your algebra. And that's, again, the key to pre-calculus is you do as much as you can algebraically, but you verify it graphically. Whether or not you graph it by hand or you graph it with your graphing calculator. Everybody get what they need out of this one? Most people are making their schedules. Okay. So reflecting even functions. This will make you happy. Prove that the graph of an even function remains unchanged when it is reflected across the y-axis. Oh boy. All right, prove, huh? This is kind of an algebra proof, but not. There's a lot of words in this. So here's what we remember about even functions. If you put a negative in, it just gets you back to the original. That's what that says. You know, I've got a negative in my function, but it gets me right back to the original because this is going to be an even function. So, how do we start? Well, prove that the graph of an even function. Well, we better start talking about an even function. So let's let f be an even function. That's how we start. They wanted us to talk about an even function. What did I know about even functions? Once I saw that, I wrote this. So, comma, by definition, f of x equals f of negative x. That's what it means to be even. So I start there. All right, so now, what am I supposed to do with this? It says an even function remains unchanged when it is reflected across the y-axis. All right? To reflect across the y-axis, what do we do again? If you want to reflect across the y-axis, what do you have to do? Where do you put your negative? Okay. Put your negative in with x. So y equals f of negative x. Okay, so I look at this and I think, is this going to work? I mean, if y equals f of negative x and f of negative x equals f of x, won't y be the same as f of x? Has it been too long for geometry, everybody? Do you remember something called the transitive property? No? The transitive property links two statements together that you know are already real. So, let's put this. However, f of x equals f of negative x for the domain of f. How do I know that? Because it's even. That's what's supposed to happen when they're even. Then, and I normally wouldn't write this step in my paragraph proof, but since you guys are not remembering your transitive property, I'm going to put this in there. Then, y equals f of negative x, and f of negative x equals f of x means, so take a peek. This equals this. This is the same as this. Can we now say that y equals f of x? Sure we can. That's the transitive property. Means, by the transitive property, y equals f of x. Pardon me, y equals f of x. Does this have a negative in it? Nope. So it remains unchanged. And that's what they wanted us to prove. The graph remains unchanged. So, gonna have to do any long-winded proofs about odd functions or anything in the homework. We're not gonna put stuff like that on the text, but every once in a while we're gonna put something like that in the homework, just to keep you guys up on your geometry skills. One of the things that people had said last year when they had to take the ACTs, our juniors last year, had said, "God, it's been so long since I talked about any of that geometry stuff. I forgot a lot of that." The other thing they said they'd forgotten was Providence stats. We don't really deal with Providence stats in pre-calculus, so every once in a while you might just want to go back and look at some old Providence stats notebooks and keep yourself up on that. So, brand new, graphing absolute value compositions. This is something we've never done. This is very cool, by the way. It says, given the graph y equals f of x, what if you took the entire absolute value of the function? What would happen? Well, the graph of y equals the absolute value of an entire function. What it does, very cool, it's obtained by reflecting the portion of the graph that's below the x-axis across the x-axis. And that leaves the portion above the x-axis unchanged. So here's what they're saying. If you have a parabola that swings down below the x-axis, anything that's below the x-axis, just kind of flip it up like a switch. And you have your graph of the absolute value of that function. Now the next one looks a lot like that, but it's not, because notice where the absolute value bars have changed. This one says the graph of y equals f of the absolute value of just x, not the entire function, just the x's. This one can be obtained by replacing the portion of the graph to the left of the y-axis by a reflection of the portion to the right of the y-axis. So with this one, when it's just the x that's being reflected, you take the stuff that's on, like it said here, replace the portion of the graph to the left, take the stuff that's on the left and replace it with flipping over the graph across the right to the left. So it's very cool. We'll see it in a minute and it'll make more sense. So like it says, portion to the right gets flipped across that y-axis, leaving the portion to the right of the y-axis unchanged. So that one's going to show even symmetry when we do it. So what we're supposed to do here is imagine just a good old parabola here, and what happens to it if we take the absolute value and see what's going on. So the graph of y equals f of x is shown at the right. Match each of the graphs below with one of the following equations and use the language of function reflection to defend your match. Note that two of the graphs will not be used, so we have some spares. So I start thinking, okay, the first thing they said was, if you do absolute value of the whole thing, you take the stuff that's below here and you flip it up. And then this is gone. So that's what this one's supposed to look like. Which one of them looks like that? C. So that one's going to be C. All right, the next one, they said kind of ignore what's on the left and just take the stuff on the right and flip it over. So I can't erase this, but I will draw over it. I'm going to take this piece and flip it over. And it'll kind of look like that. Do we have any that kind of look like that? What is it? A? Yep, only one we have. Oh my, this one's got two pieces. Order of operations says we do this first. Okay, so we already did that earlier. That would be this graph. But then there's a negative there, which means we need to reflect it again. So where do I reflect it? Oh, that's right. This came from this. So that really means, oops, that should be a line. If the negative's in front of the y, I'm supposed to reflect that over the x-axis. So take this and flip it down. Which one matches that flip down? F. One more to go. This says, all right, order of operations, go back to the one where you had just the absolute value of x. Okay, that was this one. And now take the absolute value of the entire function. That means this stuff has to go up here. So it's kind of going to look like this. We have something that kind of looks like that. What letter is it? I lost the ability to speak. What letter? B. Okay, Cedar, that's kind of weird. How much are we going to use that? Not very much. It's just kind of an interesting new thing. Are we getting close? Oh, you're kidding me. All right. Well, bad news then. You might not be able to do this whole assignment. I know. It's disappointing to me too. Do what you can. Basically, it's just page 136, 1 through 32. And like I said, you might not be able to get through all of it at this point. So if you get to the point where you're saying, wait a minute, I don't think we did that yet, then don't do it.